Okay, I think I start the recording. Okay, so let's start today's lecture. Okay, so last time, we talked about some chemical equilibrium or reaction, right? And then we try to discuss using the chemical potential or Gibbs energy, right, from that perspective. Just to quickly remind you, or refresh your memory, right? So last time, we talked about some equilibrium, right? So this is a very important concept. So when now especially for those who doing the air quality modeling or air chemical transport model, right? So you always assume there's an equilibrium, okay, between the aerosol phase and the gas phase, like for some gas particle partitioning or aerosol formation, okay. Of course, some gas phase reactions are there which can reach equilibrium. So therefore, we try to discuss this equilibrium, right, from aerosol perspective. Okay. So last time we saw this, you can have an aerosol equilibrium, right? Calculation. And then for some general equation or general reaction. So just quickly remind or refresh your memory for some general reaction. So in case we can assume you reach an equilibrium or an equilibrium state, right? So basically, you are looking at the summation, right, of this stoichiometric coefficient, right, of your species times the corresponding, right, this is the chemical potential of your species. And then if you sum them up at equilibrium state, right, this should be equal to 0, right? So we derived this last time. And of course, now you know that for these chemical potential, right? So you can also replace by the more detail, right? So for the chemical potential, right, of a species, right, at a given state, of course, this can be related to some reference state or standard state of the chemical potential of the species, times this gas constant related to the temperature. And also remember, right, so we are not using like just the pressure, partial pressure, or concentration, right? We use this we call the activity, right, of the species. So that's why, remember, so for example, for the gas phase, or the aqueous phase, so you need to find the activity coefficient, right, to your partial with the pressure or the concentration, right, to get the activity, right. So because somehow, so we need to correct the non-ideal situation. And then if we expand these terms, right, so eventually last time we stopped here, right. So because what we are discussing here is that we assume like the reaction can reach an equilibrium, right, the equilibrium state. So therefore, to describe this reaction, so you can use we call the equilibrium constant, K, right? So I think so this is the equilibrium constant, right, for your reaction, okay? So then that will be just a multiply, right, by all the, like, this is the activity coefficient times the stoichiometric coefficient, right? This is the activity. Remember, this is the activity, not just the partial with pressure or concentration. This is the activity of the species times the activity, this stoichiometric coefficient will be equal to this exponential term, right, equal to minus 1 over RT times the summation, right? This is also the stoichiometric coefficient. And then this is the chemical potential, right, of the species at their reference state, right? So what you learn from this equation is that basically for this equilibrium term, right? So I think you use this many times before, right? So when you calculate some reaction at the equilibrium, right? So reversible reaction. So basically you can calculate these, okay, equilibrium constant, right? Will be equal to this term, right? This is the stoichiometric coefficient. So this is, remember, this is the chemical potential, right, of those species at the reference state or standard state, right? So basically, you can calculate your equilibrium constant, right? If you know the reaction, right, of the reaction, and also if you know the chemical potential of the species at the reference state, and then this will equal to the activity times this the multiple this activity stoichiometric coefficient. So this is usually what these times are what you write the equation before many times, right? But now he just want to show you that, so you can also calculate this equilibrium constant, right? Using the chemical potential at the reference state. Okay, so you can also calculate this one. So maybe this is not too familiarized with some of you. So basically, what you try to do is, for example, if you consider a gas phase reaction, so that means all your species, right, are in the gas phase. Okay, so that means all the species. Okay, so all the species so involved in this reaction, right? So are in the gas. So when you look at this equation, right? So you can, I think you remember, right? So you can write down the equilibrium constant K, okay? And then now you can replace this activity coefficient, right? With, sorry, activity of the species with the partial pressure, okay? But of course, you need to correct the activities, okay? In case for the aqueous phase. So then in this case, the activity can be replaced by the partial pressure, okay? Oh, I just want to correct one of my correction. So sorry for that is so to correct this activity. So for the gas phase, so most of the time it's reasonable to just using the partial vapor pressure. But remember for the aqueous phase, okay, the activity, right? So we need to times the activity coefficient. I think we discussed last time. But for the gas phase reaction, okay, so you can just use the partial vapor pressure of your species. Okay. So usually this is what you observe, right, or you use many times, okay, in your calculation or before. Okay. So now this is basically we want to discuss about the equilibrium, chemical potential, Gibbs-free energy. So do you have any questions before? But I think the most important thing is so most of the time, so for many important process, for example, gas particle conditioning, so we assume we can reach an equilibrium state, and also for some reaction, especially for those reversible reaction, so you can also assume an equilibrium state. And then now just one more idea is now you know that this equilibrium constant, right? Of course, you can write it in terms of their partial vapor pressure and also their stoichiometric coefficient, right? Based on the reaction. But now you can also have more idea is that you can also derive from the chemical potential or Gibbs-free energy, and you can calculate, right, the equilibrium constant. If you know the reaction, that means that you know the stoichiometric coefficient of the species and also their chemical potential at the reference state. So you can also calculate the equilibrium constant. Okay. So basically, this is just to give you some more insights, okay, into some aerosol equilibrium reaction. So now we want to move on to another topic. Also, but before I move on, so do you have any questions from the class? So I think this is just something, just to remind you that you can also calculate the equilibrium constant, okay, using the chemical potential. And then give you some more idea about the Gibbs-free energies and also the equilibrium constant, right? The thermodynamics concept. So now we want to talk about some important components, okay? So I think that's a question, right, from the class. So let me see. So what is the symbol? Looks like pi and the summation, right? So I think we are talking about this symbol, right? So this symbol basically means you just keep applying to multiply all these terms, okay? For example, you can say this is maybe we can make up some idea. So you have the different species, so they have different coefficients, like stoichiometric coefficient. So basically, for example, you can just multiply, say 1, and then the stoichiometric say is 2, species 2, and then they look at the stoichiometric coefficient. So basically, just multiply. You just keep multiplying the terms. Okay, so this is simple. Okay, does it make sense? Okay, good. So basically, just keep multiplying your species with the potential here. This is the stoichiometric coefficient. Good. So of course, remember your potential coefficient can be positive and negative, right? So because again, whether it's a reactant or product, right? So if a negative, then you have a negative exponential, then you go to the denominator. Okay, good. So any other question? Yes, again, so feel free to let me know. So if you have any question, you can unmute yourself or you can just type in some magic. So in case I missed your message, so just remind me. Okay. So now we want to talk about one important aerosol component is the water. Okay. So of course, I think we spend a lot of time talking about the aerosol composition. So people talking about inorganic species, organic species, maybe black carbon, and then soot, and also some crystal materials. Okay, so all these compounds. But remember, so you can imagine, right? These compounds can also absorb water, right? For example, some salt, sodium chloride. I always want to use the sodium chloride, right? The table salt as an example, right? So in the marine aerosol, we can find a lot of sodium chloride. So like the salt. So the salts can also absorb water, right? So of course, it depends on their composition and also depends on the meteorological condition, like the temperature and also the relative humidity, right? So you can imagine you have more humid, right? And then that means your salts can absorb more water. And then if it's less humid or dry, so then the salts will absorb less water, right? Or sometimes they will become a solid. Okay. So therefore, one thing is aerosol. So we also contain a lot of we call the aerosol water. So just I want to highlight here. So this is also an important component of ambient aerosol. So therefore, for those who are interested to look at like the aerosol size, also their concentration, their reaction, their properties. So you also need to consider this aerosol here. Okay. So the first thing I want to talk about is something related to how your aerosol, okay, interact with the water vapor. Okay. So if you look at the aerosol, okay, and then you can have some interaction, right, with the water vapor. Remember, now we're talking about the water molecule, right, in the gas and water vapor. So there's some interaction. So of course, this will affect how much the amount of the water, right, in the aerosol, but will also affect the phase. Okay, of course, the one thing is like I mentioned, so this will affect the amount of the aerosol water, right? And also, it's important is that these interaction, right, between the water vapor and the aerosol will also affect the phase, or sometimes they call physical state of the aerosol. So what's that means of phase or physical state? So you can imagine, so you can have a simple case like you can have solid and aqueous droplet, right? So you can imagine, right? So if you have a table salt, sodium chloride, right? So you have a table salt. So under low RH or dry condition, it's a crystal, right? It's a solid, okay? So we call this a solid. But when you expose the table salts, right, to some water vapor under humid condition, right? So they will absorb the water, right? And then eventually they will just become a aqueous droplet, okay? So this is the cases here. So therefore, we want to study like this aerosol and also the water vapor interaction. Okay. And then there's a term to describe this. So what we call the hygroscopicity. So you can come across with this term called hygroscopicity. So basically, we are talking about so how the interactions between the water vapor and aerosol affects, say, the amount of the water or the aerosol water, okay, or the physical state of the aerosol. So in general, we call this called hygroscopicity. And then sometimes people just also use another term called water uptake. So in the literature, sometimes if you study the hygroscopicity, so someone also use water uptake to claim or to describe the interaction between the water vapor and also the aerosol. So therefore, when you study this hygroscopicity and also the water uptake, so you always come across with a graph like this. So you will see a graph like the x-axis here is the RH. So that means it's called the relative humidity. So we use the term RH. Okay. So that means this relative humidity, right, gives you some idea about the amount of the water vapor, right, in the gas phase. Okay. And then the x-axis here is usually called the particle size. Okay, so we look at how the particle size change with the relative humidity. So maybe we can start with some just a single component. So let's say we just look at a single species. We just simplify the discussion and then give you some insight. Okay, so let's say we have a single species. So for example, sodium chloride, in this case. So that means that you have an aerosol. Okay, you just contain sodium chloride. So now you can imagine, so you can have some sodium chloride, right? So this is just some aerosol. So let's start with some cycles. You see what happened. Okay. So initially, if you have this as a relative humidity, right? So you can from 0 to 100%. Okay. So if under with the dry condition, so say for example, low relative humidity. So you can imagine, right? So your sodium chloride, just the table salt is a solid, right? It's a crystal. So therefore, you can start with a particle with a solid here for sodium chloride in this case. And then you can just keep expose this aerosol to increasing RH. So you can increase the RH, right? So to your table salt or your sodium chloride aerosol. And then if you look at their size change, okay. So you can find that so when you have a dry condition, and then you increase the RH, so you will find that your particle size does not change that much, okay? So you will find that your aerosol size does not change because the aerosol or the sodium chloride, right, does not absorb any water, right? So if you have some idea, is that if the table salt, we increase the exposure to increasing RH, so right, and then most of the time you will see them, they just exist like a solid crystal, right? So they don't absorb any water, significant amount of water. But then at a certain point, and all of a sudden you will find that your sodium chloride, or crystal, right, or your salt, will absorb water all of a sudden, and then you become a droplet, right? And then a certain RH, and then you will find that your aerosol or your sodium chloride, right, will all of a sudden absorb a lot of amount of water, and then become a droplet here. Okay. So in this case, so you can have a sharp change, right? Okay, and a certain RH. So we call this a process called data crystals. Okay. We call this a process called data crystals. So all of a sudden you from a solid particle, and then you become a aqueous droplet, okay? Or more specific, this is a saturated, okay, aqueous droplet. So this process, okay, we call data crystals, okay? From a solid to an aqueous droplet, we call this a data crystal. And then the RH, okay, so at which this process happens, that means that the data crystals happen, is called the data crystals RH. So therefore, you also call this a DRH. So that means D means the data crystal RH. So that means this is the RH at which, okay, the aerosol all of a sudden absorb water, become a saturated aqueous droplet. So this is called the data crystal. So maybe let me write down here for you. So therefore, as the DRH, D here means the data crystal RH, and then the solid particle, okay. So we can argue that spontaneously so absorb water. So you can see there's a sharp, right, water uptake. And then producing, we call a saturated solution or aqueous droplet. Because this point is also important, right? So you will produce a, we call the saturated, right, at this point. Because of because you absorb the water, right, the droplet you form should be more like a saturated solution, right? Because of this is kind of the maximum, maximum concentration, right? You can achieve, and then you can argue, right? Because it's a saturated solution, right? And then if I further increase my RH, so I can absorb more water, and I will just dilute, okay, your droplet here. So therefore, more important is when you have these, you form a saturated solution, droplet. Because you can imagine, right, you just have the right amount of water to dissolve your salt, right, in this case. So therefore, you will form a saturated solution. Okay, you just have the right amount of water to dissolve your salt. So you form a saturated solution. And now, of course, you can argue, right? So if I further increase my RH, so what will happen to my aqueous droplet? So of course, if I increase my RH further, right? So my size will keep increasing, right? So I become a bigger droplet. Okay. So because when you increase the RH, okay, so what will happen is you just absorb more water, right? And then it becomes a more diluted solution, right? So you just absorb more water when you increase the RH. Okay. So now this is what happened. So when we increase the RH, are you okay with this? Do you have any comment? So you can just think about you have a table salt exposed to increasing RH. So this is what happens. So now this is an increasing RH. So you can also expose to decreasing RH, right? So then you can argue, right? So you have the same droplet. So now you're exposed to decreasing RH. So what will happen if you decrease the RH? So then you have the water evaporation, right? So now you will find that this is a equilibrium. So it will just decrease the size, right? If you're decreasing the RH, so this is increasing RH, so this is decreasing RH, your size will decrease. And then you think that, okay, when I reach this saturation point, okay, so now I will become a solid, right? So I think we also have the idea is so if we have a aqueous droplet, right? So when we're exposed to low RH or under dry condition, right? So they will give you back the table salt, right? So give you back the sodium chloride crystal, right? So when will this happen? So you may think that when your aerosol, right, is an aqueous droplet, when you decrease your RH, right? So at this point or this diffusion point, right? Because of this saturation, right? So this is a saturation point. So you think that this it just cannot overcome this saturation, right? So then it will give you back the solid, okay? But this is not the case, okay? Not always the case. The idea is for the aerosol, so even you pass through this saturation point, I think you have the idea, right? So if you have saturation point, if you're beyond this saturation point, you will start to see the crystallization, right? So the crystallization will occur. But for the aerosol, this is not the case. So what will happen is, I think you also maybe learned from some of your classes, so they will just remain as a liquid. So they will not crystalline. Okay. So they will just remain as a droplet. But now you can see that they will call this called the supersaturation because this is the point, the saturation point, right? So beyond this is we call the supersaturation. So therefore your droplet will become supersaturated. Okay, this is a supersaturated droplet. And then at a certain high condition, okay, certain high concentration, now you can trigger the crystallization process. And then this will give you back the solid here. Okay. So then for this point, okay, from a droplet, okay, become a solid. So this point, so we call this called the ERH. Okay. So E here means the efflorescence. Okay, ERH. Efflorescence. So efflorescence basically means that the term we use for crystallization. So therefore, in the literature, if you are interested in this topic, so when you do the reading, so sometimes people also call this called the CRH. C here means the crystallization. Okay, just let me write down the DRH. DRH means the depth. So usually in our aerosol science, so we use called the efflorescence RH. So basically means that you have a droplet and then you become a solid here. So this is called the efflorescence RH. Or sometimes people also call this called crystallization RH. Okay, but most of the time we use this term. And then the delicacy means that you have a solid particle and then you delicacy, right? Or you become an aqueous droplet or saturated a solution aqueous droplet. So this is called the delicacy. So therefore, for a single species, okay, like you will see, this is how single species aerosol, so they will behave, okay, in response to the change in the ambient relative humidity for single species. Okay. So maybe I just highlight a few points. So remember, so when you have this solid, you have this delicacy process. So this is called the saturated droplet. So you form a saturated aqueous droplet. Okay. So but remember, so when passing through this saturation point, okay, so you will not crystallize. Okay. So you will go through this that we call supersaturated. Okay. Supersaturated. Okay. Droplet. And then after certain high concentration, and then you have this crystallization can happen. Okay. And also most of the time, these term, right? So because ideally, so you think that when you go through this, when you're decreasing also you follow the same line, right? So this is not the case. There's another term we call this called hysteresis. So I think you've also heard this from some of your hysteresis. Some of your physical chemistry classes. Okay, so because you will not always follow the same lines, so you see this we call the hysteresis phenomenon here. Okay. But the idea is that this is like a typical cycle of a single species aerosol. So you see this, so you start with a solid, and then you put delicacy, form its aqueous droplet at a certain point. So we call this called the DRH. Okay, and then we can also crystallize, right? And then if you have a solid particle, so this is called the efflorescence or crystallization. So we have this ERH and ERH, and then you have this is called the particle size change. Okay, so when you do to absorb your water. So do you have any questions right now? So then I think one of something you may puzzle, right, in your mind is so why you don't have this crystallization, right? When we just beyond this, we call the saturation point. Okay, so there's some reason. The reason is so if you pass through this saturation point in an aerosol, so because you're free of any physical contact, if you want to all of a sudden lose all your water, okay, say so it's very challenging. It's very difficult. Okay, so therefore, even the beyond or pass through this we call the saturation point. So you can think about so you all of a sudden you need to lose all the drop of water, right? So at this saturation point, okay, so it's very difficult. So therefore, you always have this we call the hysteresis. So we need to keep losing some of the water, right? Okay, and then eventually to reach a certain high concentration, then you can trigger the crystallization. So therefore, the crystallization here you do not be very significant. Okay, process. So therefore, these are some terms. So when you describe the hygroscopicity of an aerosol, so you come up with this one. This is related to we call the phase, we call the transition. Okay. Sometimes this is called the phase transition. So basically means you can have solid to a aqueous droplet. So we call this is called the delicacy. Okay. And then also you can have a supersaturated aqueous droplet. And then it can become a solid, okay, in this case. So this is called crystallization, right? Okay, or called the efflorescence. So this is called phase transition. Okay. And then the size change here. So this is related to the amount of the water you uptake, right? So most of the time, so the size change here. The particle size change. Sometimes they call hygroscopic growth. So because this particle size change is due to the water uptake, right? So uptake of the water vapor, right? So this is called the hygroscopic growth. So usually they will take a ratio. So when you look at this hygroscopic growth, I just give you an information when you do the reading in the literature. So you will see a term called they call the growth factor, GF. So most of the time, so to describe this water uptake or hygroscopic growth, right? So they will use this called the growth factor, GF. So they define this the particle size. You measure the particle size at a given RH, and then you compare to the particle size at a reference RH. So usually it's a dry RH or low RH. So basically you compare to a RH, the size of the particle at a low RH, and then you measure how the particle size change, okay, at different RH, and then this is the size change, right? So this size change is due to the water uptake. That means the amount of the water you absorb by your aerosol, right? So this is called the growth factor, okay? And then these terms are called the phase transition, okay? And then this is called the hygroscopic growth. And also, I think the more important is for you to remember is now when you're decreasing the RH, I just want to highlight one more point, is when you're decreasing the RH, so you will not do the crystallization here, okay? So you will go through these, you will have this, we call the hysteresis phenomenon, okay? So you form this supersaturated solution, and then at a certain point, there is this crystallization happen. So this is the typical phenomenon you will see when you study the hygroscopicity of a single species, okay, in the aerosol phase. So you see something like this. So I just want to give you some typical number for some important species. So of course, different species. So different species, right, will have different RH, right, different properties, right, or different interaction with the water vapor. So we can argue also for different species. Okay. So they will have a different ERH. Right, so we have different DRH, right? Delicacy point, sometimes we call or DRH. Just for example, we just talk about the sodium chloride. So the DRH will be advanced. So this is the relative humidity. Okay, so this is the DRH for the sodium chloride. It's about 75% RH. So that means that if you have a solid, okay, sodium chloride aerosol, okay, when you increase the RH to 75%, and then you will find the aerosol, all of a sudden they will absorb water and become a saturated solution property at this relative humidity. And then you can also have this we call the ammonium sulfate. So these are some important ambient, okay, salts. So this is around 80% RH. And just one more is the ammonium nitrate. So this one is around 61% RH. Okay. And also, just want to highlight something is for some species. So if they exist in aerosol phase, so you will find that if this is the RH, and then this is their size. So basically, we have the same figures here: the RH, the relative humidity, the particle size. So you will find some species, okay. So you don't have this kind of a sharp change in your particle size, right here. So for some species, I just want to highlight because somehow they can have very strong chemically bonded water molecules. Okay, they have a very strong. So they are not likely to lose their the water weight, the water molecule. So they will have these kind of a smooth curve, right? So you can see here. So therefore, I just want to highlight is that for some species, okay, in the aerosol phase, so they does not say exhibit both the deliquescence and also the efflorescence, okay. So you will not see any deliquescence or crystallization or efflorescence here. So basically, just the more exists, just like a aqueous droplet, okay, all the time. There's always an aqueous droplet with different concentration, so you don't have any, say, the phase transition in this case, okay. So one typical example is important for this is there's another term in the literature for this species called non-crystallization or non-crystalline species. Okay, so that means that they're always aqueous droplet. So one of these important species, one example is important is sulfuric acid. Okay, so sulfuric acid. So there was always we can argue, right? So notice phase transition. So that means that always there's a water is always associated with them. Okay. So you always have the water. So even at very low RH, so they still can retain the water at very low RH. For example, sulfuric acid. So therefore, here just to give you some very typical cases. Okay, so when you study like the hygroscophicity of a single species, remember now we talk about just a single species. So later we talk about multiple components. But do you have any questions so far? So I think this giving you information, then you have some more ideas. So in case that if you do the reading, right, in the literature, so you have some more ideas about the aerosol hygroscophicity, like the terms. Okay. Okay. So we can also, one thing we are interested to look at is the phase transition. Is so we want to know at a certain RH, right, at a given RH. So we want to know so whether your aerosol or your species, right, are solid or liquid. So one thing we are interested to look at is say at a given RH, right? So at a given RH. So we want to know so whether your aerosol, right, for example, sodium chloride, so whether they're solid or liquid in this case, or aqueous droplet, right? So we want to know so whether they're solid or aqueous. So of course, if you know the DRH and also your ERH or CRH, so now you have some idea about the phase, right, of the aerosol at a given RH. We try to understand these, just to give you some example, is try to understand this using the Gibbs energy we just discussed, right? The Gibbs energy. So you can draw a graph here. So for the y-axis here is the Gibbs energy of your system. Okay, so you have the Gibbs energy of your system. And then the y-axis here, sorry, the x-axis here is your relative humidity. Okay, so because I want to look at, so at a given RH, so whether your aerosol, right, or your species, that means your system. So it's a solid state or it's an aqueous droplet, right? The solid particle or aqueous droplet. So you can look at different relative humidity. So say this is 50, 60, 70, 80, 90, close to 100. Okay. So now if you look at the Gibbs-free energy, G here means is the Gibbs-free energy of the system. So for a solid particle, so if you remember, right, for the solid particle, the Gibbs-free energy, so it's independent of the composition, right? So it's always a constant line. So you have a constant line. It does not depend on your relative humidity, okay? So therefore, this line is the solid particle. So this is the Gibbs-free energy of the solid. So it's independent of your aerosol composition. Right? That is, it does not dependent on the relative humidity. But you know that for the chemical potential, right? Or if you remember, right? So for the aqueous solution droplet, right? The chemical potential or your Gibbs-free energy of the system, right? Will depends on your aqueous phase or your solution composition, right? So therefore, you can imagine, right? So the Gibbs-free energy for your aqueous solution, okay, we change, right, with the relative humidity. Okay, using this line. So this will be your aqueous solution. Of course, you are showing constant temperature and pressure here. So this is how your Gibbs-free energy, right, of your aqueous solution change with your RH. For example, the idea is when you increase your RH, right? So that means your solution become more diluted. Okay, so then for this system, so the Gibbs-free energy will decrease. Okay. So now you can see by looking at this point, okay, so we can have some ideas about the physical state of your system or your aerosol. Okay. So one thing we can see that, so somehow you have an intersection point here. Right? So you have an intersection point here. So let's say it's about 80%. Okay. So now you can argue, right? So for example, below this point, okay, below this point. So what will be the state? So for example, so let's say your RH, so it's less than this intersection point, say 80% RH. Okay. So if you look at the system, okay, the Gibbs-free energy, right, of your solid, right, is lower than your Gibbs-free energy of your aqueous solution, right? So you see here, right? If you look at that corresponding, at RH below 80%, right? So in this case, so the Gibbs-free energy of the solid, right, will be lower than the Gibbs-free energy of the aqueous solution, right? The corresponding, right, aqueous solution at that different RH. So therefore, we notice that so for the system, right? So we always want to have a minimum Gibbs-free energy. So therefore, you can argue, right? So below this 80%, right? So the solid is the preferable state, right? So that means your species, right, will be in the solid state. So you can argue the Gibbs-free energy of your solid, right? Solid state will be less than or lower than the aqueous state, aqueous droplet. So therefore, we know that the system, right? So we want to have this the solid state. Okay, and then now you can see that if we keep increasing our RH, right? So let's say if we just have this RH, say larger than 80%. So what will happen now? This is just the opposite, right? So that means your Gibbs-free energy of your solid will be larger than the Gibbs-free energy of your aqueous droplet, right? Corresponding aqueous droplet. So that means that now we know that, so the aqueous state, right? Or the aqueous droplet is the preferable state, right? So in this case. But so therefore, right at this point, right? Right at this point. So let's say the RH equal to 80%. So you will have this we call the transition, right? So we have the transition, right, from the solid to liquid. So therefore, we can argue, right, this RH, we just will be our DRH, right? That's 80%. So in case you know the gypsy energy of the system, okay, a solid at different state, so you can calculate, right? And then this is the intersection point. So now in this case, so you know this is the transition, right, from solid to liquid, okay. So therefore, this is just what we talk about is to a delicacy, right? So this is the delicacy. So this is the where. So this point is the where you have the solid on the aqueous droplet. Right, so we just discussed here. So this is just the we call the delicacy point. So you have this. So therefore, this RH, right? So we just mentioned here, right? So this RH is just called the delicacy point, or we call the DRH here. Okay. But remember, so this graph is the more you can use to determine the we call the delicacies. Okay, so we can predict these using this gypsy energy. But remember, so there will be a problem, right? So in case you do the opposite, right? You decrease the relative fluidity, right, from high RH to low RH. So then you will argue, right? So this will be the crystallization point, right? So this is also the phase transition will occur, right? So, but remember, so this is not the case, okay? Because this is not purely governed by the thermodynamics, okay? So in this case, so just I want to highlight is so this graph is just used to predict the delicacy point, and then because when you pass through this, like we mentioned, right? So this is because somehow all the water, right? So you can argue at this saturation point, all the water, so needs to evaporate, right? So this will be very physically difficult, okay? So therefore, in this case, so they will still remain, remain as a droplet, okay? So therefore, no transition will happen in this point, like I mentioned here, until you reach the high concentration. So sometimes we call them, there's a point, it's called the critical supersaturation. Critical supersaturation. Then in that case, okay, if you remember, crystallization happen means that you have some nucleation events happen, right? So therefore you have some nucleation can occur. So that means you can have the crystallization happen. So therefore you will have this called the efflorescence here. So do you have any questions so far? So these are just give you some ideas. So in case for those you want to interest to do the modeling, okay, so we want to calculate, okay, for your system, so what's the phase state of your system, okay? So different components, right? You have different species, concentration, different temperature, pressure, or relative humidity. So basically, what you try to do is to calculate the gypsy energy of the system, okay? And then you try to find, okay, the minimum, okay, the global minimum, the gypsy energy of the system. Okay, then that will be your state. Okay, so now you have some idea about the phase transition, the water uptake. Okay, I want to continue to spend more time, or to spend some time on the water, also water. So one thing we want to talk about here is we call the chemical potential. chemical potential of water in aerosol. So there's some reason we want to study the chemical potential of aerosol in water. Okay. So first, we want to look at, say, the water. Now you know that in the atmosphere, so some water will be in the gas phase, right? So therefore, you will have some water vapor, right? This is the amount of the water present in the gas phase. So if you look at the amount under typical conditions, so you are talking about maybe gram per m cube. So that means that in 1 cubic meter of air, okay, so you will have grams, okay, of water vapor. But of course, this will change, right? Depends on your relative humidity. Okay. And then you have some water, right, in the aerosol phase or in the aerosol. So most of the time, so it's only around milligram, order of magnitude, or even less, or microgram. Okay, so you have a milligram to microgram. Okay, in 1 cubic meter of air. So that means that your aerosol, right? So it can contain some water, right? So the aerosol water, okay, will be just about milligram. So then, if you look at the order of magnitude here, okay, so you can find that like this water uptake, right, by the aerosol. So even you have some water uptake or transport, okay, some water vapor transport across like aerosol and gas. So they will not affect the ambient, right, water vapor pressure or the amount, right? Because you can see by just looking at the qualitatively, right, you look at the order of magnitude, right? So the water uptake by the aerosol, so under most of the typical condition, right? So you will not affect the amount of the water vapor, right? So therefore, you can argue, right, the transport of the water, right, to or from the aerosol, right? So would not affect the ambient, right, amount of water vapor or the water vapor pressure, right? Okay. So that means, so most of the time, then we can argue, right, is the ambient average, okay, so would not be affected. And then your ambient average, so even you consider this water uptake, can be assumed to be constant, right? So this will not affect or can be treated constant, right? So because it will not affect by the water uptake of your aerosol here. Okay. So now we can talk about some gas particle partitioning, right, of your water vapor, of your water. Okay. So then you can argue, right? So you can have some water uptake. So therefore, you can argue the water, right, the partition, right, between the gas phase and also your aerosol phase, right? So that means because of some water will be in the gas phase, some will be, say, in the aerosol. Okay, I put that acreage means because you have a water, right, in your aerosol, then we can say it's an aqueous droplet, right? So if you don't have any water in aerosol, it's a solid, right? Dry solid particle. So but here just AQ means you just have some. This is some water, right? Will be in the aerosol phase, and then some water will be in the gas phase, and then they can reach a kind of an equilibrium, right? So this is how we can assume there's an equilibrium. And then if we assume you can reach an equilibrium, so what will happen is the chemical potential, right, of the water vapor, of your water molecule in the gas phase will be equal to the chemical potential, right, of the water, right, in the aerosol phase. So this is how we define the equilibrium, right? So this is how we reach the equilibrium. Okay. So now you can also write down the equation, right? So you, for example, like this chemical potential, right, of the water vapor in the gas phase. So you can write down you can extend this equation, right? For understanding right down here. So this is the chemical potential of your water molecule in the gas phase will be equal to the chemical potential of the water molecule in the gas will be equal to the chemical potential of the water molecule in the aqueous phase at equilibrium, right? And then you can expand these, right? This is the reference state, right, of the water vapor, right, in the gas. If you remember, and then this will be equal to the RT, right, times the natural loss of PW here means is the partial vapor pressure, right, of your water vapor or your water vapor pressure. Right, so this is your partial vapor pressure of your water molecule or your water vapor pressure. And then this will be equal to, this is your aerosol phase, this is the aqueous, right, solution, you can argue. So this will be the chemical potential, right, of the water, right, in the aqueous solution, right, the standard state, plus the RT, so this is the activity, right, of the water, okay, in the solution. If you remember now, this is your so this is your water activity, right? In the solution, that means that in your aerosol phase here. Okay. So now I want to do some substitution here. So for this equation, okay. So let's say, so assume we have a pure water droplet. Okay, so if you have pure water droplet, so now you know the water activity will be equal to 1 because it's just the ideal solution. So your activity will be equal to 1. And then at the same time, the vapor pressure, right? So you will have is what we call the saturation, right? Water vapor pressure, right? So this partial, this is a PW naught is the saturation, right? Water vapor pressure, right? Because you are looking at the pure water, right? And then you measure the water vapor pressure. So with pure water, so this would be just your saturation, right? Water vapor pressure, right? Also you measure the pure water. And then if I substitute this into here, so you will find that so because if I substitute these, say for pure water, right? So your activity, right? Your water activity will be equal to 1. So this term will become 0, right? So this term becomes 0. And then your partial or your water vapor pressure in this term will become your PW naught, will become your saturation water vapor pressure, right? P naught. And then if you rearrange this equation, you will find that, okay, so your chemical potential of your water, right, in the solution at reference state minus the chemical potential of your water, right, in the gas state at standard state. So this is two terms, the difference will be equal to RT times the natural log, the saturation water vapor pressure. So since I have this expression, right, this term, I can substitute this term into this back to this equation. So by doing this, so you will find that, and then we arrange this equation. So what we can replace these two terms, okay? This will be equal to RT times the lateral loss saturation water vapor pressure, right? So if I substitute this one back to here, so you get this term. So what's that mean? So again, so this is the water activity, right? So again, this is the water activity. In the aerosol phase, right? So this is the water activity, aerosol or aqueous solution. If you look at this term here, so this is the partial vapor pressure of the water, right? Water vapor. So this is the saturation water vapor pressure, right? So what's the meaning of this ratio? This is the saturation water vapor pressure. This is the partial, right? Partial vapor pressure of the water molecule, right? So this ratio is just what we call the relative humidity, right? If you remember, by definition, right, relative humidity, right, is just the amount of the water vapor pressure, right? The amount of the water vapor, right, divided by the saturation, right, water vapor pressure. So this is just the relative humidity. Okay, then now you may ask, so why this equation is very important? So one thing is, you can see here is, for example, you try to do your model simulation, okay, or you want to calculate the equilibrium. So let's say you want to have some equilibrium calculation. Okay, equilibrium calculation of your aerosol, your ambient. Okay, you do your simulation, okay, but then you need to somehow you have some parameter to be constrained, right, or to test so whether your result is correct or not, right? So now you will find that is if you don't do this calculation, right, assume the equilibrium, so you can always find that at a given average, right, in your simulation. So you will know that your water activity is fixed. Right, so because we show you here, right? So at an equilibrium, right? So at a given average, so the water activity is fixed, right? So you can just correlate it. So therefore, with this condition, okay, so now you can constrain your simulation, okay, or you can check so whether your simulated results are correct or not, because at a given average, okay, for your model simulation, right, your water activity has to be fixed, right? So that will be related to this term, right? Because at the given average, your water activity, right, in your aerosol, okay, is fixed. So you can use this as a condition, right, to check so whether your simulation is correct or not, right? Because for your model simulation, right, your water activity is fixed, so it needs to be equal to the ambient average, right? So therefore, this is a very important information. So this will help you to do your simulation. To check whether your simulation are correct or not. Okay, if you assume there's an equilibrium calculation, okay, for your ambient errors in your models. So do you have any questions so far? So, but the idea is, now you notice that at a given relative humidity, okay, so then you will know the water activity, okay, in the aerosol. So then you will have this relationship. So do you have any questions so far? Okay. So again, so feel free to ask a question, let's say during the break or after the class, okay? So I overrun a little bit for the first section. So let's take a 10 minutes break here. Then we'll come back at 12:50, okay? So let's take a 10 minutes break here. So in case you have any questions, so feel free to ask during the break. So we'll come back at 12:50. Oh, okay. So in case the homework, may I see if the TAs is here? Let me see. So I would suggest that if you have any questions, so I would direct you to asking the TAs. Is that okay? Yeah. Because I don't have the homework assignment with me right now. So, but you can just send him a message. Okay. Okay, so maybe we can resume the class. So, but before we continue, so do you have any question from the class? Any question? So one thing here is just to give you some more ideas. So now you can see if you know the relative humidity, right? So now you will also know the water activity in the aerosol. Okay. So this will be very important, okay, especially for those who run the model simulation, okay, for aerosol thermodynamics or water uptake. So this is important because you have this constraint, right? So if you set the relative humidity, so that means your model output, right? So your water activity has to be equal to your relative humidity, right? So this is fixed, okay? So this is that's why it's important. And also, if you have this idea about, so the water activity will be equal to the relative humidity, right? So you can also argue, right, like the DRH, the deliquescent RH, right? So then that will be equal to the water activity, right, of the saturated solution of the salt, right? Am I correct? So because if you remember what the deliquescent means is that you have a solid, and then you become a saturated solution, right? Droplet or aqueous droplet, right? So this is called the deliquescent, right? So DRH is the RH, the relative humidity, right, at which the deliquescent happens, right? So then that means that the DRH, okay, so that would be equal to the activity, right? The water activity of the saturation solution of your droplet, okay. So therefore, you can somehow, if you can calculate, right, the water activity, and also you know the solubility of your system of your species, then you can calculate the water activity at the saturation point, and then you can that one, right? So you know the water activity will be related to the ambient RH, right? Oh, okay. So there's a message. So what's the physical meaning of the water activity and what is used? Okay, good. So if you remember, right, so if you look at how to say the activity. So now when we say water activity, so for example, in this case, so this is called the water activity, right? So that will be equal to what is the activity coefficient, right, of the water times, for example, the molarity or the concentration, right, of the water, right? So this is actually to say to correct the non-ideal situation, right? Telling you really how's it related to the chemical potential. If you remember the chemical potential we just showed you, right? Is some standard state, and then plus the RT, right? And then you're looking at the concentration, right, of the water, right? And then because you know, we also need to consider the kind of the non-ideal situation, right? Because we always have a concentrated solution, right? So it's not always an ideal solution, right? So you will deviate from this equation. That's why you need to consider, like, the idea for this water activity coefficient is to correct, like somehow the interaction between your water molecule with other species, right? So this will cause you deviate from the ideal solution. So therefore, if you really want to look at the chemical potential, so more precise is you are not just looking at their concentration, right? So it will be true for diluted or ideal solution. But if you really want to look at the chemical potential, right? Okay, for your concentration, you need to always consider the deviation from the ideal situation. So you need to have this activity coefficient. So that's why we are looking at the activity coefficient. Does it make sense? I try to answer your question, yeah. So because the idea is you can use the concentration, right, of your water, right? So you can measure this. You can use the concentration of your species, and then you can somehow calculate your chemical potential. But this can only apply so when you say it's like the ideal solution. Okay, so that's why people want to introduce these activity coefficients to correct the non-ideal situation. Okay. So that's why you can have better representation or presentation for your chemical potential. Okay, good. So any other question? Yeah, so sorry for that. I think the water activity. So I think last time we talked about the aqueous solution, right? So we talked about is the concentration of a species, right? So now you can imagine you can use the water, right? You can just like the species. So we talked about last time. Okay, good. So therefore, if you come back to what we just discussed here, is now if you can calculate, right, your activity, your water activity, right, of your saturated solution, that means your water activity in your saturated solution, then that one would be just equal to the RH, right, the ambient RH, and that one actually would be just equal to your direct RH. So that means if you calculate your water activity, say it's about 0.8, okay. So that means if you go back to this equation, this is 0.8, and then you times 100. So that means the data percent, the DRH of your salt will be 80% RH. Okay, so this is how you link these two together. So this is just one example. So we want to have some more discussion about this data percent RH because these we call the phase transition, right? So this is data percent. Or this we call phase transition if you're interested. Okay. So this is important, right, for us to understand. So in a given RH, so whether your aerosol of the salt is a solid or is an aqueous droplet, right? So it's important. And also this data percent process actually is temperature dependent. Okay. So this is also temperature dependent. So that means B is the RH, the percentage. So whether it's 80%, 85%, so this will also depends on the RH, okay? So that means that the DRH will vary with temperature. Okay, so we're going to look at this process here. So if you look at this data percent process, we can actually think about two processes. Okay, so one is first you will have some water, right? The gas, and then you dissolve into the aerosol, right? So this is the first process. So you have some water, right? Transport from the gas phase to your aerosol phase. And then the second step is so now you have some water, right, in your aerosol phase. So they will dissolve your salt, right? So let me follow my notation. So now you have some water, right? And then you can dissolve your salt, okay? You put NS. And then now you become aqueous saturated solution. So that this process, right? So I think we know this process. So you have some salt, you have some water. So basically just a dissolution process, right? You dissolve some salt. So this is a dissolution, okay? And then S is your solid, N is like a, because remember, right, when you have this data percent, so you are looking at just a saturated solution, right? So therefore, this N, to form a saturated solution, right, this N will be the solubility, right? solubility. Okay, so because this will give you the saturated solution, right? Solubility basically means this helps you to determine, right, the composition at your saturation point. So this is called solubility. Okay. So of course you can always argue, right? So this is actually, so when you have a gas transport, right? You have the water vapor transport from the gas to the aerosol. So this is called condensation, right? So you can also have a name for this process. So this is just called the condensation of water, right? And then you have this dissolution of your salt. Okay. So therefore, for the overall enthalpy change, right? So you need to consider these two processes. So therefore, the overall enthalpy change. So that means that somehow we need to consider these two processes. So we just have delta H. So basically, you just have this enthalpy change. You have this kind of enthalpy of the solution, and also this kind of a condensation or vaporization, depends on the notation you use. Okay, and it's because I say if this is this solution, so say per mole, you just times n, right? N is the number of mole of your solute, right, at the saturation point. You just put an n there. Okay. And then if you know this overall enthalpy change, right? So basically, just consider these two processes. Okay. So then you can just have the change. And then you look at how the change, right, in the water vapor pressure, right, over a saturated solution droplet will be just equal to this term, right? I think you have seen this Capron equation before. So this will, if you solve this equation, so this will tells you so how this will change, okay, with the temperature. So let's say this is the change in the water vapor. So that basically this equation, I think you said this before, is to look at how the change in now is the water vapor pressure, right? Over a solution, so within a certain temperature change. So related to the overall enthalpy change, and then divided by the RT here. Okay. So most of the time, so we can just we skip the details. We just want to show you that the delta% point. Okay. So if you have a delta% average, you want to know at a given temperature, so you can compare to the delta% average at a reference temperature. Okay. So that will be equal to, maybe let me save this space. So now if you solve this equation, so you look at, say, how the delta% average change with the temperature, and then you can compare to the delta% average at a reference temperature. So it will be equal to delta HS. So this equation so you can use this equation to calculate how the direction change, okay, with the temperature at a given time temperature. So T naught is your direction temperature determined at the reference temperature. So usually the reference temperature in this case it can be determined at 298 Kelvin. Okay. And then this is the delta HS is the heat of the solution. And then R is the gas constant. And then this ABC is a coefficient that you can apply for different species. So that different species, so they will have different coefficients. And then tells you how the DRH change with the temperature. So because of different species, right, they will have a change to different extents. One crucial parameter, okay, will be affected by this coefficient is the solubility. Okay. So how you come up with this ABC? One thing is the solubility will also change with the temperature. Okay, so most of the time people describe the solubility of a species. Okay, it's changing with the temperature using an equation like this. So that's why when you look at the delicacy change with the temperature, right? So of course, you need to look at the heat of the solution. So usually it will not change between the temperature, like the ambient temperature. But the ABC here, so mainly it's come from the solubility. Okay, because you know the solubility of your solution, right, can be sensitive to the temperature. So therefore, your saturation point will be different. Okay, so that's why you come up with this coefficient. But one thing is just to give you some information. Okay, so for some common salt. Okay, so let's say DRH versus temperature. So just to give you some number, okay, for some common salts. For example, we have always talked about ammonium sulfate. Let me write down here. So for some common salt, for example, this is ammonium sulfate, and then at different temperature. So you will find that so we have a three temperature. Maybe let me write down in this way. Okay. And then you look at your ammonium sulfate. So you're looking at the DRH, the delicacy RH, okay, for a pure ammonium sulfate aerosol, okay. So at different temperature. So you will find that so at 0 degrees Celsius is about 82%. And now you drop to 80.6, and then 79.5, 8, sorry. And then maybe the other one important, maybe ammonium nitrate. So you also see that at lower RH, at lower temperature, you have a higher DRH. So one thing is you can see is that when the temperature increases. So the only message is that you can see when the temperature increases. So you will find that your delicacy RH will decrease. Okay. So why would this happen? So you can see here when we increase the temperature, right? And then the delicacy RH actually decrease. So why this happen? So one thing is because when you look at this process, okay, or the solution, the overall enthalpy change. So you will find that this delicacy process overall is an exothermic reaction. It's an exothermic reaction. Okay. So overall, it's an exothermic reaction. So therefore, for exothermic reaction, so we know when we increase the temperature, right? So it will decrease, right? The pH will decrease. So basically, the idea is that overall is an exothermic process. Okay. So therefore, this is why you observe this one here. So any questions so far? Okay. So now we have this. You can see here, right? So we show you if you have a single species, for example, sodium chloride, then you will expect you have a sharp change, right? And then you have a continuous growth when you increase the RH. When you decrease the RH, so you will not crystallize. When you have a supersaturated, and then you crystallize, right? At a critical supersaturation, and you give it back to solid here. So this is a single species. Okay. So what will happen if you have a multiple species? So you have A or B. So you know in the ambient, right? So you can have ammonium sulfate. You can have, for example, in this case, it's ammonium nitrate. So they can coexist, right, in your aerosol. So therefore, your aerosol can have more than one species. So how would this delicacy point change, or this graph change here? Okay. So therefore, one thing here we want to say, if you have, say, multiple components, so that means that you can have more than one species, right, in your aerosol. So multiple component aerosol. So we want to look at, so what would be the delicacy? Okay, so what would be the delicacy change? So with that delicacy change here, okay. So how this delicacy point will change? So you have two species. So we will still see a single sharp change, or how this pH change will increase or decrease. Okay, if you add another species here. Okay. So we want to do some qualitative argument here. Okay, to help you to understand. So let's say if you have multiple component aerosol, so how would the delicacy process change? How would it change? Okay. So let's say we just consider a system. You have two species. Okay. So first, let's say we consider. So you only have two species in your aqueous solution. So you actually have two species. Consider two species. Say 1 and 2. Okay, in your solution. That means that we present in your aqueous solution. Okay. And then what we want to do, what we want to discuss here is, so we want to see, so how the change of the DRH, the delicacy point, the DRH, okay. So how the DRH, okay. Say if you only have one single species or single solid, aqueous solution, okay. So let's say now because we have two species, right, in our system. Say when another species, say that means 2, is added. So that means initially we can argue, so for your system, so initially you only have one single species, right? Then you have a sharp, right, DRH, a delicacy point, okay, here. So now what will happen to this DRH if I add another species, okay, into your system, okay. So now if we add another system, so we can try to discuss this, okay, by looking at like the gypsy energy, okay, or how the change in their chemical potential. So we look at the change in their chemical potential. Okay. So if I add some species right into the system, of course, the chemical potential of my system will change. Okay. So in this case, so let's say we simplify our discussion. Let's say we also consider at a constant temperature and also pressure. Okay, so in that case, so when I add a species into my system, right? So of course, my chemical potential or my GMT energy, right, of my system will change. And then eventually, if I assume, so we can reach an equilibrium state, okay? So I can find out with this equation. So let's say if I add a species into my system, okay. So of course, although we are mentioned, we have two species in my system, but because we have an aqueous solution, so we also have the water. And then at equilibrium state, okay, so we notice that from our GMT energy, or we call the GMT energy equation. So you will find that, so this will be related to the amount of the species one, and then look at how their chemical potential changes because I add a species into my system. And then plus the concentration of my species two, and then how the chemical potential change, right? And then plus, remember, so we also have the water. So let me, I don't put the W3 here. So this is the water. So this is the amount of water, right? Because in my system, right? So remember, initially, so I will have my system, right? With just a 1, 2, and just one, but you remember, so you also have the water around. And now eventually I will add 2 inside, right, to your system. So we have 2 here. Sorry, we have 2 here, and then 1, and then also the water. Okay. So this is how we can define the states. So let's say if we can apply this to our system. Okay. So let's say we consider a case like this. We set some initial condition. Okay. So first, because we want to look at the change of the DRH of a single salt, right, of the aqueous solution. So when we add another species, right. So let's say at the beginning, so you have the species one, right? So your species one is in equilibrium. So with this salt one. Okay. So what's that mean? So that means that initially, so you have a solution, right? And then you have a species one, okay? And then you are in equilibrium with the salt. So that means so you will add a lot of salt, and then eventually this solution becomes saturated, right? And then because you have excess salt, then you will see some presence of the salt, right? So in your system. So that means that now you know this is your salt one. So now you know your solution will be saturated, right? Because you have the salt present. Okay, you have some excess salt. And then this solution will be saturated solution, right? With respect to the species one. So therefore the DRH, so this will be the DRH, right? So the water activity of your solution here will give you the DRH of your species one. Does it make sense? Because now this solution, right, is a saturated solution, right? With respect to the salt one, that means your species one. So therefore, the water activity, right, of this saturated solution will be the delicacy, okay, or the DRH, okay, of your salt or your species one here. Okay. And also you can see at the beginning, so we only have this species one, okay, in equilibrium with this salt. So we don't have any species two yet, okay. So now, so what will happen is, so when I add some of my species two, so now I can add my species two into my system. I can add my species two to in my system. So you can also argue, right? So we only add initially, so we only have a very small amount of your species 2. So therefore, your species 1 still remain in equilibrium if it's a solid phase. So your species 1 remain in equilibrium. Say with this solid phase. Right. So basically, you still see the solid, right, of the species 1. So if I just add some species 2, right, so you still reach equilibrium. Okay. So if you agree with this argument, right, so when I just only add a certain amount of my species 2 into my system, and then it will not affect the equilibrium, okay, of the species 1 between the solution phase and also this solid phase. So therefore, you can argue in this case, the chemical potential, right, the chemical potential of my species 1 does not change, right? Because nothing happened, right? That does not change my equilibrium, right, for my species 1, because you can argue we only add very small amount, right, of your species 2 into the system, you will not affect the equilibrium. So therefore, if you're okay with this argument, so now this term, okay, so will be just equal to 0, right? Because your chemical potential will not change. So you can, in this case, so I can argue the chemical potential of my species 1 does not change in this case. So now my equation here so can be reduced to so nothing. I just drop out this term here. Okay, so don't worry about it. And also, if you look at this chemical potential, if you remember, right? So for solution phase, for the chemical potential for a certain species, right? So you can just expand this equation, right? So remember, for the solution, right? So you use this activity, right, of the species. Okay, this is the chemical potential of the species at reference state. So if you substitute this one into this equation, and then to replace the chemical potential, you will find that you will get so you just substitute this into this equation, and then you will just find that now it becomes the concentration of your species 1, then B, this is the natural norm activity. Remember, this is activity of your species 1 plus the number of mole of your water, and then this is changed natural norm. This is the activity of your water, okay, in this case. So now we want to change a little bit of the unit. Remember, so when we talk about the activity, right? So it's the activity coefficient times a concentration term. And then the concentration term, so usually we use is the molarity. Okay, so therefore, so this is, sorry, 2 should be. Sorry for that, because this is the species 1 is 0, right? So I draw out the species 1, so we have the species 2 in this case. So sorry for that. So I just want to change to this to the molarity. So in this case, I'll express the terms in terms of molarity. So then if I take the ratio of these two, this is the number of mole of my species 2 to the number of mole of my water. I also want to express this into the molality of my species 2. So I will write down the equation like this. So this MW is the molecular weight or the molar mass. Of the water molecule. So this M2, so I introduce this M2 is the molality of my species 2. So if you remember, by definition for this molality is the number of mole of my species per kg water. Okay, so I just change this, introduce this term. So then I can just substitute this into back to this equation. Okay, so if I rearrange this equation, so I just we will find this equation will become M2 So that's nothing. I just play around. I just try to introduce this molality into this equation here. Okay. So given we are interested to look at so how the activity, right? So because now you know, right, the activity of the water will give you some idea about the delicacy, right, or the delicacy knowledge of my solution, right, of my system. So if I rearrange this equation, so I can rewrite this equation like this. So what I'm trying to do is I just put this on the other side. I just multiply the terms to the other side. So don't worry about this. It's just rearrange this equation. Okay. So now one thing is we want to know, right? So how the DRH of my solution will change, right? When I add species of my species 2 into my system, right? So that means the water activity will change, right? So therefore, in this case, so you can argue, right? So I can add certain amount of my species 2, say from 0 at the beginning, I have no species 2, right? And then I add to certain amount, say M2, okay? So then in this case, I can take the integration and then look at how the water activity change, right? So let's say so maybe let me write down the equation and then I'll explain this to you. So this equation just tell us, let's say initial I don't have any species 2, right? And then I add, right, from 0 to certain amount, say M2, okay, the concentration from 0 to M2. M2 is the molality of my species 2, right? So initially it's 0, and then I add my species 2 into my solution, right? So then the concentration will change from 0 to M2. So this will be how the water activity will change. And also this will how the activity of my species 2 will change. Okay. So remember when I add this, so my species 1 is always in equilibrium, right, with my species with the salt. So therefore we don't need to worry about this. So then I can integrate this one, right? So I can integrate this one. So I can integrate this one, then you will get that. So your water activity. So these terms will tell you so how the water activity will change, right? So from 0 to M2. So will be equal to, I know this is a long equation. So let me write down here. So if I look at this term, so this is the natural log activity 2. So I apply a change rule, okay? So because I want to take the integration, right, from 0 to certain amount of, right, molarity, right, of my species 2 here. So I can change this one using the change rule. So basically, just because I want to take the integration, so look at how the change, right, of the species 2, right? So from 0 to n2 here. So I can apply the change rule. So in case you're interested, so this one is equal to. So I think this would be just 1 over alpha 2 times the d alpha 2, right? And then if I apply the change rules, I can just multiply. So that's why I can substitute this into the terms here. I put down this alpha 2 because the activity, right, of my species 2 would be depends on this concentration. Right? So then if you look at this equation, okay, so maybe let me rewrite this equation. So just rewrite this equation like this. So don't worry, I just rewrite the equation just to make my discussion. So this equation just tells you, if you look at the left-hand side here, so this is tells you, so how the water activity, right? At the beginning, you don't have any the species 2, right? And then you add some species 2 to certain concentration. This is M2 is the molarity, right, of the species 2, right? Say from 0 to M2, right? And then of course your water activity will change, right? In this case, okay, this will be equal to minus. It's a minus sign here. This is a molecular weight of my water molecule, right? Divided by 1,000. This is how the concentration range. So now you look at these terms on my right hand side here. Okay, we just want to look at the sign. See what happens. Okay, look at the sign. So of course you will find that this is to be positive. So adding this is also positive. So now is one thing is I want to look at this term. Okay. So what's the meaning of this term? So this term is telling you, so how your water activity, right, of the species 2 change, right, when you add some species 2 into a system, right? So this is how the activity change, right, when your concentration change, right? So this is by definition, okay. So in reality, so it turns out that people find that for this term, okay, this term, in general, so in general, so people would find that the activity of your species 2 will increase, okay, always increase with your molarity. Okay. So if this is the case, so that means that this will be positive. So when your molarity increase, right, the change in your activity will also be increased. So this term will become positive. So therefore, this term will be positive. Okay. Just for qualitative argument here. So if these terms are positive, so you can argue, so the whole terms here will be also positive, right? But remember, you have a negative sign here, right? So you have a negative sign here. So therefore, your right-hand side, the whole term. So now the whole term on your right-hand side, okay? This is positive, so this is a negative sign. So that would be negative, right? So your sign would be negative. would be negative. So what's the meaning of negative? So if this term is a negative, so that means the water activity, right? If you look at this is a negative, so that means this term is the water activity, right? So when you have a certain amount of your species 2 will be lower than your initial value, right? So that means that if the whole term is a negative, you agree with me, this term will be always positive. So the whole term will be negative. So if the whole term is a negative, so this ratio, you will find that your water activity will decrease. Okay. So that means maybe more precise, helps you to understand. Will decrease. Maybe down the word, that means the activity of water decrease. Okay. In this case, when species 2 is added. Okay. So if we have come up with this conclusion, okay, so your water activity will decrease when your species 2 will decrease. So given if you remember, right, the water activity, so will be related to the RH, right? And also eventually you will relate it to the DRH of your system. So therefore you can argue, right? So the DRH of your system, right? If you have a multiple component, in this case, 2 species, right? So it will be lower than your pure component because when you add 2 here, so your water activity will drop. Okay. So therefore your DRH will also drop. So therefore the idea is so when you look at this argument, so when you add some species into this, and then eventually you make this saturated with species 2 as well. So you will find that the DRH of a mixture, okay, will be always smaller than the DRH of the single species. So this is just to give you some qualitative idea. The idea is that because of due to some the ion interaction, okay, so you will always observe this phenomenon. Okay. So therefore, now we go back to the question. You said you get the DRH. Okay. So this is your single species. Okay. So then if you add another species into your system, okay, so then you will see that your DRH will always shift to your left-hand side. Okay. So when you add another species here, so you will see another, maybe here, something like this. So your DRH will shift to the left. So you have a lower DRH. Okay. That's the point. Okay. Any questions so far? So I think the key message for this one is when you have a single species, okay, so if this species exhibit a sharp, okay, phase transition, say in this case, you have a sharp stereochroism process and also a sharp crystallization process. But usually this is the only you observe for a single component, okay, single species. So in case in your system, okay, if you have a multiple species, okay, so you will not, usually you will not see a very sharp, okay, phase transition like this. Okay, you will see multiple steps, okay, something like this. Okay, we also try to help you to understand some phase transition, maybe using some phase diagram. Okay, so this will help you to understand some phase diagram. So again, we use the 2 species as an example. Of course, you can extend to multiple species in your model simulation. Then you just make the phase diagram more complicated. But we just show you the key idea and also the concept. Okay, by using a binary system. Okay, and then later you can extend this to multiple components. Okay. So again, here we just want to show you to understand some phase transition or deliquescent, okay, using a two or maybe binary system, okay. So in this case, we show you, say, if the system, you have some ammonium nitrate, and then you have some ammonium chloride. Basically, you have the two salts, okay, and then we want to look at just the deliquescent process, okay. So try to understand. I think you've seen this phase diagram before in other classes, but we just try to use these to try to understand like the deliquescent or the phase of the aerosol. In this case, it's just a two-salt system here. Okay. So maybe let me draw the phase diagram and again I will explain to you. So give me some time. So. Okay, so sorry, it took me some time to draw the phase diagram here. Okay, so let me show, have some discussion about this phase diagram before we take the second break. Okay, so now if you look at this X and Y axis, so remember, so we have a two-salt system. So we have ammonium nitrate and also the ammonium chloride, okay. So if you look at these on the x-axis here, this is the mole fraction of my ammonium sulfate. Okay, so ammonium sulfate. Sorry, ammonium nitrate. So what's that mean? So this is 0. So that means I don't have any ammonium nitrate. That means that if this is 0, that means I have. Maybe I can draw the other one. So this will be my pure ammonium chloride, right? So this will be my pure. So I only have pure ammonium chloride in my system. And then this one on this right hand corner here, right? So then I have my pure, right? So this will be my pure ammonium nitrate, right? And then this one, I have my pure ammonium chloride, right? And then the y-axis here is the water activity, okay, at saturation point. So I can measure the water activity and a pure species or different composition, and then measure the water activity at their saturation point. So that means this will ideally give you the ideas about the deliquescent point, right, of my species here. Okay. So before we take the break, so we just want to extend this very quickly. Okay. So if you look at these points, so I have a 0, right, amount of my ammonium nitrate. That means I have a pure ammonium chloride, right? So therefore, this point, right? So this point. So this will give you the Delaplacian point of ammonium chloride, right? So this will be your DRH of ammonium chloride, because you have pure ammonium chloride, right? So this will be the DRH of my pure ammonium chloride. So this now you know, so this will be the DRH of my ammonium sulfate. Okay. And then now you can see that by this phase diagram, so you have some idea. So we're going to talk about after the break, but you can separate, right, this graph into different regions. So I can have some dotted line here, and also I can have a dotted line there. Okay. So you can have a different phase, right? This is the what activity of the saturation of your system, right? So you can have some different region, right? You can separate this graph to different region, and then to understand the phase of your system, right? Of your two source system. So we're going to talk about this maybe after the break. So maybe let's take another maybe another 5 minutes break. Is that okay? So we will come back maybe around 5:53 maybe. Yeah. So let's take we come back at 5:53 and then we'll talk about this phase diagram. So to help you to understand the phase of your two systems at different composition, okay, and also so what would be happening. So we're going to take another break here, okay. So we'll see you in about 6 minutes, okay. Okay, so maybe we just continue. And then today I think I will try just to finish this phase diagram, okay, before we leave. So if you look at this phase diagram again, so remember this fixed axis is the mole fraction of my, this is the ammonium nitrate, right? So then you have ammonium chloride, so just opposite. So that's why you have the pure ammonium chloride on this end, and then you have the pure ammonium nitrate in the other end. And since this graph, the y-axis here, we talk about is the water activity, right? At the saturation point. So this will give the delicacy, okay, average of the system. So you can argue, right? So this line here, so I think also you have some ideas that this line will give you some idea about the composition, right? Of the solution, right? Of the liquid or the solution, right? So, but how to understand this phase time? Okay, so let's look at this. So, for example, let's say just think about this point, right? So let's say it's at this end, okay. So in this end, so we only have ammonium chloride, right? So then, therefore, this point, like we discussed, right? So this point will be the DRH, okay, of this pure ammonium chloride, right, of the particle, or of the aerosol, right? So therefore, in this case, we can see maybe it's around 78%. So sorry, this is close to 0.8, but it's about 78% average. And then for this system, so usually we make this assumption, okay. So when this RH, so let's say it's larger than the DRH, so we know, right? So for pure solid, right? So you have an RH larger than your delicacy point. So then it will become an aqueous droplet, right? So therefore, it is a solution, right? And then in this case, because it's a pure, right, ammonium chloride, so you only have a pure solution with ammonium ions and also the chloride ion, right? Because remember, we are talking about only pure ammonium chloride, right? So here. And then if your RH, say now, below the delicacy point, but in this case, so we are just assume you have the type of solid. It's a solid type. Okay. So therefore, if you look at this graph, so we can see this is the delicacy point, right, of my pure ammonium chloride. So what we have to know about this RH? So for all composition, so you can see all composition, right? So this delicacy RH is below the DRH, right? Of my pure salt, right? If you remember, we just discussed if you add another salt to the system, right? Your delicacy of your mixture would be lower, right? So therefore, it's always a lower. So therefore, you can see your RH is larger than the delicacy point, in this case, the ammonium chloride. So this one, the region A, is always a liquid, right? So no matter your composition, right? So this is just a liquid. So in this region, okay. So therefore, you can see in the region A, right? So in the region A, so given the RH is always larger than the delicacy RH, or your ammonium chloride, of course, it will be larger than the delicacy, right? RH or DRH of your ammonium nitrate. So therefore, you can see that the aerosol is a solution, right? It's always a solution. And then it depends on the composition, right? So you can have ammonium ions, you can also have chloride ions, and also you can have nitrate ions, right? So because you always have this nitrate here. It's okay, right? So for region A. So now we move to this intermediate region. Say, see if I can use different color. So say this is B. So the region B, okay. So in this region, maybe let me highlight B. This is A. But you can see for the B, for this B region. So depends on the composition. So you can have two different behavior, right, or phases here. So let's say this is the left-hand side of your line, because this line will give you the composition of the liquid. And then this is your right-hand side, okay, of your solution line here. So let's see what happens. So if I define this the left-hand side, this area, okay, for my region B. For my region B, now I'm looking at my left-hand side. So how I define this left-hand side? So this is within the DRH of my ammonium chloride, right? So your RH is less than the DRH of your ammonium chloride, but above the DRH of your ammonium nitrate. Right, so this is how I bound this region, right? Okay, so this is above, it's below the DRH of the ammonium chloride, but above the DRH of my ammonium nitrate, right? So what will happen to this case? Okay, so in this case, so you know that, so there will be some solid plus liquid, right? Because if you remember, right, below the DRH of my ammonium chloride, right? So I will have some solid, okay? So because in this case, right, if my RH is below the deficit point, so you will have some solid here. So therefore, in this region, right, so you will have some solid, and then together with liquid, right? That means you together with the solution. So therefore, in this case, in your aerosol will consist of, because now the RH is below the deficit RH of my ammonium chloride, right? So therefore, you will have some solid, right, ammonium chloride. And then in equilibrium, so with a solution, right? And then your solution, so you will have some ammonium ion chloride and also the nitrate ion, right? Does it make sense? Okay, so below this you have solid, but you have some ammonium nitrate, right? And then this ammonium nitrate is above the DRH, so you have some solution. Okay. But what will happen to your right-hand side? To your right-hand side here. So right-hand side, you can see that is somehow this is in the liquid region, right? So how we can understand this? In your right-hand side. So you can always argue, right? So of course here, so you somehow, when you move to your right-hand side, so what will happen to the composition of your aerosol? So you will have a more ammonium nitrate, right? So you can see, right, on your right-hand side. So in this region, right? So you will have more ammonium nitrate. Okay. So what will happen is your ammonium nitrate, right? So because it's always above the DRH, so you dissolve, right? So with the solution, so you have an aqueous solution, so it dissolve. So you have the water, okay. So therefore, in the right-hand side, so what will happen is that you have enough, or you're given enough ammonium nitrate because it's above the deficit point, right? So this ammonium nitrate, right, can also result in this we call the complete dissolution, right, of your ammonium chloride because it's above the DRH of the ammonium nitrate, right? So you dissolve and then provide some water, and then that water, right, that amount of water can also dissolve your ammonium chloride, right? So you can argue, right? So this will result in complete dissolution of ammonium chloride. So therefore, you always have a liquid phase here. So therefore, your aerosol is always a liquid or aqueous solution. Of course, you will have ammonium, nitrate, and chloride. So you can think about this here, okay? So of course, you just have a pure ammonium chloride, right? So then you add, then when you move to the right-hand side, so you add some ammonium nitrate. But most of them are sodium chloride. So of course, you have a lot of sodium chloride solid, but you have some ammonium nitrate, right? So they will dissolve, and then you can here, right? But so therefore, you don't have much liquid because you only have very small amount of water, right, come from the ammonium nitrate. But in this region, right, so you can argue, right, so you have a lot of ammonium nitrate already, right? So then they will have a lot of water, right? And then that amount of water, you can argue, also can dissolve your solid ammonium chloride, right? So therefore, in this case, okay, so therefore you can have the pure aqueous, right, just the liquid. Right? Because you have a lot of ammonium nitrate, they dissolve in water, right? And then they can provide the water, right? Or to dissolve the solid, right, ammonium chloride if they present. Okay, so therefore in this case, here is also the liquid. Okay. So therefore you can also follow the same lines here. So you always notice that on the left-hand side of the line, so you will also have you always have the liquid or solid. Okay. So now you can have a free region. So you can see in this region C, all right. So you can separate into free region. So you can have maybe this is 1, 2, and 3, right? So you can have 1, 2, and 3. So they will have different behavior. So if you look at the region C in 1, okay, so because you're still below the DRH, okay, of the ammonium chloride, you have lots of ammonium chloride there. So you know that, so you will have C say 1. So you will have a solid ammonium chloride, right? So not surprising. And then you also will have some solution, right? Because it's above the DRH of the ammonium nitrate. Okay. So in that case, you have also have a solution of ammonium, okay, nitrate, and also chloride. Okay. And then, but in your region 2, okay, so now you can see that you don't have any solid phase, no solid. Okay, and only you have a solution. Okay. And you have a solution phase. Of course, you have the same ions here. And then you can have 3. So now you can argue why it looks like this. If you're in the region 3, right? So what will happen? Now it's below the DRH, right? Of course, remember in region C, your RH is below the DRH of your ammonium nitrate. So you can form some solid of ammonium nitrate. So in this case, close to the right-hand side right here, you have a pure ammonium nitrate, or most of the aerosol, right? The component ammonium nitrate, they behave more like ammonium nitrate, right? And also below the DRH. So therefore, you will have pure, you have some solid ammonium nitrate. But of course, you can have some solution, right? And then your solution phase, we just have all these 3 ions here. Because some of this will be dissolved, right? And because remember, when you have the pure ammonium nitrate, right? So you can also apply the same argument we studied, right? So if you add other species, right, into the system, right? So you will decrease the DRH, right? So you also decrease the DRH of the pure component here. So basically, this is a help you to understand the phase diagram. Of course, you below this point, right? So you below this point about 50%. So now you only have the solid here, right? So in this case, in the region D, okay, you just have the solid. If the RH is low enough, then you just have the solid here. And then one last thing is you see there's a minimum point here, right? So we have a name for this minimum point. Okay. So this is called the Newtonic point. So this is called the Newtonic point here. Basically, mean this Newtonic point is corresponding to the minimum, okay, DRH of your system. Okay. Of course, this will depend on system and also their composition. So this is called the Newtonic point. Kind of you can see is the minimum point, right? It's the minimum DRH of the system. Okay. Of course, this point will depend on the system here. So do you have any questions so far? I think it's easy. It's okay to understand, right? Say above the high RH, just above the DRH of the ammonium chloride, right? So basically, it's an aqueous phase, right? So then if below this Newtonic point, it's just a solid phase. Okay, in between, so that will be depends on your composition. Okay, it will be depends on the composition. But here the idea is when you have more and more ammonium nitrate. Okay, remember ammonium nitrate has a lower DRH, so therefore they always have delicacy. So this will help you provide some water to dissolve your salt. Okay, so I got a question from. So may I know what would be fine for C2? Yeah, right. So, okay. So if you look at the C2 here, so that's a question from. So if you look at C2, right? So this is in the liquid phase. So therefore, you will find no solid and only solution. So this is the solution phase. Okay. So no solid. And then there will be liquid. So remember, this is a liquid. So sorry, this is a solution. You have a liquid here. Does it make sense? Yeah. So that means that if you look at your diagram, so the line here, right? So that the liquid will still extend to here. So sorry, because there's no liquid, and then you still have the solution phase here. So it's a solution. Yeah. Good. So, but I think the overall message for this graph is you can see, say above a high RH, of course, you have a pure solution phase, and then at low RH, so you have a pure solid phase. But in between, so that means if you look at the aerosol, okay, I just want to highlight this. That if you look at this diagram, don't worry too much about so where they goes, but I hope that you have some idea is that when you talk about the aerosol, if you have a multiple component, so you will always have some liquid, you can have solid, and then in between, you can have some solid liquid coexist. So this is, you are not always looking at a pure liquid or pure droplet solid here. Oh, okay. So why we always have this some solution? We always have this ammonium nitrate, right? Because you can see, right? So if you are on these two ends, you only have pure ammonium chloride and pure nitrate, right? So that means that right? So you just a solid. If you dissolve, you just have ammonium chloride or ammonium nitrate plus some water. But if you just move away a little bit, so you add some sodium chloride. So what will happen to the sodium chloride? So because of the sodium chloride, so ammonium nitrate. So sorry, if you just move away from here, so you add some ammonium nitrate to the system. Because the ammonium nitrate, right? So have a low DRH, so it's always above the DRH. So this ammonium nitrate will dissolve, right? So you can think about this, so they will just dissolve because it's above it. So therefore, you form a solution. Okay, and then some of this solution you can argue, right? So you have some water come from the ammonium nitrate, but this water can also dissolve some ammonium chloride, right? So therefore, you also give you the chloride. Does it make sense? Even most of your ammonium chloride is in solid phase, but if you add some small amount of water, right? So some ammonium chloride will also dissolve into the water. Does it make sense? So therefore, your solution will always have some chloride also. Do I answer your question? Okay, good. Because you remember, so when you add, of course, it's a pure ammonium chloride, right? But then you add some ammonium nitrate. So what will happen to your ammonium nitrate? So they will dissolve, right? And then will give you some water. Okay, that water, you can also argue the water come from the ammonium nitrate can also dissolve some, not all, but dissolve some ammonium chloride. So therefore, you give some your solution. So you also have some ammonium chloride. So you can intuitively think about this thing. Okay, good. So do you have any other questions? But I think the key message for you to, of course, when you add to multiple components, then you see in the textbook, right, the phase cycle become very complicated. Okay, sometimes you cannot even display too many dimensions. But I just want to highlight is that, so of course, we always talk about an increased droplet or a solid. But here, I hope that you also bear in your mind, you have some ideas that for multiple component system, so you can always have solid coexist with the liquid. Okay, so you are not just talking about pure increased droplet, pure solid, so you can have solid liquid coexist, okay, in the system. So that will have some implication for some of your reaction or gas particle positioning or calculation. Okay. So I think this is very much I want to cover for today's. Okay, how about the region D? Yes, so in the region D, just the solid of ammonium nitrate and ammonium chloride. You're right. Yeah. Yeah, good. So this is the solid D, just the solid of your two salts. Yeah, good. Any other question? Okay, if not, I think that will be the end for today's lecture. Then I will see you next week. Okay, so of course you're welcome to stay behind if you have any questions to ask. Okay, if not, then I will see you next week. Okay, bye bye.